Hello and welcome to the Motech YouTube channel. In this video, I will explain what collinear axes are in CNC machines. We'll take a look at how they work, where they're used, and why they're so important for precision in manufacturing. So stay tuned to learn more. Enjoy the video. Let's start by taking a look at what collinear axes actually are. Collinear axes are when linear axes can be moved in the same direction. Now here we have an example from this machine. This is a large machining center. On the one hand, we have the z-axis, which moves in the z direction. We also have the v-axis, which moves in the same direction. And we even have the w-axis, a quill in the z-axis, which can also be moved. That means all these axes actually move in the same direction, namely the z direction. You might now be wondering, what do you need this for? Well, I always try to work as stably and consistently as possible, but sometimes I truly want to reach into deeper areas with my specialized tool, Inco. For example, I would machine this surface like this, in this case. But I might also use this very same tool later on to create this internal pocket on the inside. Now you can already clearly see with the naked eye that the head would be far too big to properly fit in there. How exactly do I control these collinear axes? Well, we have the machine running in the background here, and when I go into a machining operation, I've actually prepared this housing here for that, and I've already placed a machining operation on this front surface. And if the machine is able to manage the collinear axis, then this field actually appears here, namely the control of the machine axis. When I click on it, I can now see how the individual axes are set. That works for me as it is. I specify that the z-axis, the z1 axis, which controls, should be advanced. The w-axis should remain at a fixed position of 0 millimeters, and the v-axis should stay at a fixed position of 300 millimeters. Let's take a look at the whole thing for the second example. I have a pocket here now. I can see the current state of the machining process. That means the z-axis is currently in the process of moving, the v-axis is completely and entirely retracted, and the w-axis is also precisely at its intended and designated position at this very moment. If I now imagine that I would have to plunge all the way in with this head here along the z-axis, it would probably result in a collision. I don't even need to look at the simulation for that now. And here too, I can now go to the collinear axis and say, the table can stay at 300 millimeters, and I could theoretically enter 400 millimeters as well, and immediately see what happens here. The table moves a bit backward. But I could also say that I want the quill to extend out here in the very middle now, because I truly want to work with the quill in this particular area. But the controlled axis is still the Z1 axis. That means I have set a fixed value here, for example, exactly 750 millimeters, and I can now clearly see directly how the quill precisely plunges in there, so that we have a very detailed simulation here. And then accordingly, we can perform this machining here with the quill. I also have an example here of a long turning lathe, for instance. It could also happen there that we have the z-axis here, where the part shifts in the bushing. And we have a z3 axis, which is this workpiece holder, and they also move in the same direction. If I now, for example, go to the machining, I again have this menu for the collinear axis. And I could say that the axis to be controlled is the Z1 axis. That means it performs the movement. And the Z3 axis should remain at a fixed position of 0 millimeters. So if I simulate this, I would have a completely normal, long-turning operation where the bushing is now the one making the movement. In some cases, however, you might want to perform a particular kind of short-turning operation even on a Swiss-type lathe, where the part moves out and then the Z3 axis then performs the movement accordingly. So how exactly do I achieve that? It's simple. I go to the collinear axes and specify that my controlled axis is the Z3 axis, and the Z1 axis is now fixed at a value of, let's say, 50 millimeters. Let's run it once. I confirm that with OK, and if we now look at the simulation, the part moves forward and the Z3 axis performs the movement. There can also be situations where, for example, you say that the Z3 axis is the controlled axis. The Z3 axis is the controlled axis, but this value remains empty and is not fixed. That can happen because one axis is set on top of the other axis. I've actually prepared an example of this and I'll run it now. In this case, it works like this, that here, the first distinct channel, which precisely cuts the thread at the very front, and the second separate channel, which accurately cuts the thread at the back, and they are stacked on top of each other. So that means I have a collinear axis that is mounted on another controlled axis. And as a direct result, we get a complex movement that looks very complicated, but it is actually incredibly simple and fully programmed, and entirely predictable. Good. With that, we've reached the end of this video. I hope you enjoyed it and were able to learn something about collinear axes. We'd appreciate a comment and feel free to leave a like. See you next time.